Now that we have learned about what a derivative is and we know how to find the derivative using the limit process, fortunately for us, there are a number of shortcuts or rules in calculus that allow us to find the derivative pretty efficiently. And there are a number of them. These are the ones that I want to highlight here. So the classic one is the power rule. And the power rule pretty much works as follows. The idea is that you can take the power, whenever you're finding the derivative of the function, you could take this power that exists here and multiply it by the coefficient of x. And then you're going to decrement that power by 1. So let's take a look at this first example here. So f of x is equal to x to the fourth. So if I'm finding the derivative of f of x, f prime of x, all I need to do here is take this exponent and multiply it by the coefficient of x, which is 1. So I can just write 4x. Now, next, I'm going to decrement this power. I'm going to reduce it by 1. So this now becomes x to the third. And it's as simple as that. And there are a few more rules with this. The next one is the idea of the constant rule. The derivative of a constant is always equal to 0. And that makes sense because you're really just applying the power rule here. If, for example, I ask you to find the derivative of 2, for example, understand that this is the same thing as finding the derivative of 2x to the 0. So if I a 0 power, so if I use a power rule here, 0 times 2 is equal to 0. And after that, it really doesn't matter what I'm doing with my exponent. Anything times 0 is going to give me 0 there. So it makes sense that the derivative of any constant is just going to be equal to 0. Let me just write that. It's just equal to 0. So let's try that with number 2 here. So with number 2, if I'm finding y prime, again, I'm going to apply the power rule here. I'm going to take this exponent, I'm going to multiply it by the coefficient here, so negative 2/3 x. I'm going to decrement this power by 1, so negative 2/3 minus 1 is negative 5/3. And then the derivative of this constant, 200, is just 0. So we're all done. So that's just negative 2/3 times x to the negative 5/3. There's also the scalar multiple rule, and the idea here is if there's a scalar in front of a function, you can just move that to the outside and take the derivative of the function first and multiply it after that. And again, if we see something like, for example, number 3 here, because we haven't learned the quotient rule yet, it might be helpful for us to look at this and rewrite it so we can see the scalar on the outside of that function. In other words, that is to say, write this as negative 1/2 times t to the negative third power, since that exponent is in the denominator. In which case, h prime of t then is equal to the derivative of 5, that constant is just 0. I'm going to take this power, multiply it by negative 1/2, that's 3/2, and then I'm going to decrement this exponent. So this is t to the negative fourth power. And you can also write this as this is the same thing as 3/2 times t to the fourth. Okay? And the final one here is to say that the sum, or the derivative of the sum of two functions, is equivalent to finding the derivative of the first function and adding that derivative to the derivative of the second function, or the difference, depending on what you're doing. Okay, well, let's try a problem now that puts a few of these rules together, something like number 4. Pause the video and give that one a go when you get the chance. And this one, if you've had a chance to now work on it, f prime of x, well, by the way, again, this I can write as 5 times x to the negative 2. So this would just simply be negative 10, x to the negative third, plus 6x, which we can alternatively also write as negative 10 over x cubed plus 6x. All right, so these are some of the basic differentiation rules that we start using pretty early in this course. And sorry about the typo there. I should say examples, not whatever else was spelled there. So I'm going to move that for my own sanity. All right, so now that we've talked about some basic differentiation rules, now let's discuss differentiability. So now that we know what limits are and what continuity is, we can now have a pretty firm definition of differentiability. And in fact, I'm actually going to clean this up here and actually rewrite my notes. So we say that a function is differentiable at a point or at a c value if the limit of the difference quotient exists. And notice I'm using the alternate definition of the derivative here. And this implies that the following must be true in order to classify that a function is differentiable. First off, f of c must be, I'm going to rewrite this as continuous. The function must be continuous at the point c. So that's my first condition. My first condition is that the function must be continuous there. And the second condition is that the right-sided limit of the difference quotient must be equal to the left-handed limit of the difference quotient. That is to say, the derivative of the right, as we come from the right, must be equal to the derivative as we approach from the left. In other words, that derivative of the difference quotient must exist. So my two conditions: one, my function must be continuous at that point, and the limit of the difference quotient, aka the derivative, must exist at that point. So let's hone in right now on a couple of examples here. And in each of these examples that you see, you'll notice that all of these actually are not differentiable at x equals 1, but for different reasons. So let's go through them. So first off, let's actually zoom out a little bit here. Let's look at these first two. Let's look at this first example. We see that the function is not continuous at x equals 1. Therefore, by definition, it is not going to be differentiable there. So because it's not continuous at x equals 1, it's not differentiable there. What about the second example? Well, again, this function is not continuous at x is equal to 1. We have a non-removable discontinuity, also known as a jump. But because it's not continuous at x equals 1, it's not differentiable here. Let's move on. What about these next two examples? Let's look at this vertical asymptote here. Another example of a function that is not continuous at x equals 1. So I don't even have to worry about thinking about the limit of the difference quotient. Now, where we see this sharp turn here for this example, this is our first graph or function, I should say, where we see that it is indeed continuous at x equals 1. So by definition, that first condition has been met. However, look at the limit of the difference quotient as we approach from the left. Let me write this. The limit as x approaches this difference quotient, or as x approaches our difference quotient f of x minus f of 1 over x minus 1. From the left side, well, what does that look like it's equal to? It looks like it's equal to -1. The slope of this tangent line appears to be -1. Now, and actually let me put this in red just so we can match this. Okay, so the limit of this difference quotient as we approach from the left. Now compare that to what's happening here on the right. The limit as we approach from the right, this difference quotient's limit, well, this is equal to +1. These are not equal to one another. So because the limit of the difference quotients from each direction are not equal to one another, the limit of the difference quotient does not exist. And if that does not exist, then it is not differentiable there at x equals 1. What about our last example here? Well, at x equals 1, is the function continuous? Yes. Is the limit as we approach from the left equal to the limit as we approach from the right of the difference quotient? Sorry, let me be very clear. The limit of the difference quotient as we approach from the left, is that equal to the limit of the difference quotient as we approach from the right? And the answer is yes, they both look like they're infinity. But that last word is what's important, the fact that it is infinity here. The limit of the difference quotient it does not exist because it is infinity. And remember, a limit cannot be equal to infinity. So this is what's known as a vertical tangent line. So be prepared moving forward if I ask you to state why a function is or is not differentiable, to state the reasoning using our definition of the derivative. It is not sufficient to simply just say sharp turn or vertical tangent. You're categorizing the type of graph there, but we need to be able to use the definition of differentiability to make sure we understand why a function is or is not differentiable. So I encourage you to pause the video right now and try these examples here, numbers 5 through 8, and state where the function is not differentiable and make sure you understand why. All right, next up in talking about derivatives, we want to talk about higher order derivatives. And I'm not going to spend too much time on this, just really be familiar with the notation. The idea here is that if you can continue to take the derivative of a function. So for example, let's do an easy example, like something like x to the 4th power, right? So suppose that's my function. F of x is equal to x to the 4th. Well, my first derivative of this is simply 4x cubed. And if I can take the derivative of this again, f double prime of x, right? That notation is now I'm finding the second derivative, which this would be 12x squared. And if I can find the derivative of this derivative, then I would now write this as the third order derivative, in this case, is 24x. And so the idea is that certain functions, you can continue to take the derivative. These are known as higher order derivatives if we can continue this process. And I just wanted to highlight, literally just highlight the notation here so that you are familiar with that. And we'll do a lot more work with higher order derivatives later in this course. The final thing I wanted to discuss as we close up this lesson is to discuss the types of rates of change. And we've actually already talked about this. So just make sure that we're clear and we understand what we're discussing when we're finding the derivative. The first derivative of a function is indeed a function. The first derivative is a function that represents the slope or the instantaneous rate of, oh, there's another typo. Sorry about that, change. The instantaneous rate of change. All right, so the first derivative of a function represents the instantaneous rate of change. It tells you the slope of the tangent line at that given x value. So for example, if you find f prime of 4, what you're finding there is the slope of the tangent line at x equals 4. So that gives you the rate of change in that moment, which by definition is a little bit of a paradox, but that's a discussion for a later date. Now compare that to what we call the average rate of change. Now the average rate of change is simply what we know as our traditional slope, what we've learned up to this point as the vertical change with respect to the horizontal change. So anytime you're just finding the slope, which if you remember, this was the slope of the secant line, that is our average rate of change, or AROC for short. When you hear me say IROC, I'm referring to the instantaneous rate of change, which is the slope of the tangent line at a specific point using the first derivative. So a couple practice problems here. I'll do one with you here. Let's try number 9. Okay, let's do number 9 together. So for each of these functions, we're going to find the derivative. We're going to find the derivative evaluated at a specific x value, and then we'll find the average rate of change. So part A, let's find the derivative. We're going to use the power rule to say that our derivative here is just 2x. Okay. Now part B, I'm going to evaluate this derivative at 3, which is 2 times 3, which is equal to 6. And make sure we understand what we just found. We found the slope of the tangent line at x is equal to 3. This is our instantaneous rate of change. Now part C. Now let's find our average rate of change, which is just our slope, which is the slope of our secant line, which is f of 11 minus f of 3. We're finding the y values at 11 and 3 respectively, and we're comparing that change to the horizontal change, 11 minus 3. Well, let's look at our function. What was our original function? X squared minus 5. So we're going to say f of 11 is 11 squared minus 5. F of 3 is 3 squared minus 5, and we're going to compare these two. So if I'm going to do some quick evaluating, that's going to be 116 minus 4, all of that over 8. That's 112 over 8. And if I can do my math correctly, that's equal to 14. You can leave your answer as 112 over 8. That's fine. But there's our average rate of change from 3 to 11. The instantaneous rate of change at x equals 3 was 6. Now, one more type of problem I want to do is writing the equation of a tangent line. So we know that we can use the derivative to find the slopes of tangent lines. Let's take it a step further and find the equation of that tangent line at a specific point. So here we've got x squared plus 3x minus 5. So we know that this is a parabola. So what we're trying to do is at the point 2,5, we know that there is a tangent line there. What we're going to do is we're going to find the equation of this tangent line. What is this equation? Well, let's do that. Well, first, in order to find anything about our tangent line, I need to know the slope of the tangent line. So let's use the derivative. So f prime of x is 2x plus 3. There's our derivative. Now, I'm going to evaluate my derivative at this point, so using my x value, this is 7. Ask yourself what you just found. This is our slope of the tangent line. So I'm now going to use point slope form, which is y minus y1 equals mx minus x1. Actually, I should leave a space here. This is our slope. So this is what's known as point slope form. I've got my slope, so I'm going to write 7 here. And I know my point was given to us. So this is 5 and this is 2. And this is everything that we need to write the equation of this tangent line here. All right, so hopefully this lesson was helpful in understanding a little bit more about what it means for a function to be differentiable and how we can use that derivative to give us information about both the instantaneous rate of change and in other cases the average rate of change.